Hello and welcome to Electromagnetics 1. Dr. Trample here. This is lecture 13, and today we'll be talking about the magnetostatic version of Ampere's law. Well, again, by way of review, we're transitioning from electrostatics to magnetostatics, and here you see, again, I've reproduced the equations of electrostatics for you. And here we have the equations of magnetostatics. We're going to be focusing in on the first one here today. This is Ampere's law, the magnetostatic version of Ampere's law, and it is one of the curl equations, one of Maxwell's curl equations, which is to say the curl of the magnetic field is equal to the electric current density. This quantity here has units amps per meter squared. This quantity here, the magnetic field, has units amps per meter. Well, let's dive in now to the magnetostatic version of Ampere's law. Here is, again, the differential form of Ampere's law. The curl of the magnetic field is equal to the electric current density. If we integrate both sides of this equation over some area like this, we're certainly free to do that. Let's examine what happens here on the right hand side first off. When you integrate an electric current density that has units amps per meter squared over some area S, you're going to get a quantity that has units of amps itself. So on the right hand side here, when we simply evaluate this integration, we're going to get this term, which is just simply the current that is flowing through that particular surface. On the left hand side, we need to apply Stokes' theorem, and once we apply Stokes' theorem, the left hand side becomes the following, which is Ampere's circuit law, or Ampere's circuit law, however you want to think of it or say it. It's the same thing. What this is saying is that if I integrate around a closed path, I've shown a closed path here in this diagram in the upper right. So what this is saying is if I have some electric current density that flows through a surface bounded by a closed path like that, then if I integrate the magnetic field all the way along that closed loop, I will obtain the total current flowing through that loop, essentially. This loop is called an Amperian contour, or a closed contour. Well, let's see how we can use Ampere's circuit law to solve some practical problems. The first one I'd like to look at here is the magnetic field due to an infinitely long line current. So let's imagine here that we've got a wire, essentially, that's aligned with the z-axis. It's of infinite length and it carries a current I amps, capital I amps, right? How are we going to figure out what the magnetic field is due to this wire? Well, we have to argue, we have to use some symmetry considerations when we make our argument. The first thing, again, is that this geometry, if you start out here at a particular radial distance away from the line, a particular value of rho, this geometry looks the same, again, no matter where you are on this particular circle here. Any circle enclosing the wire looks, is so long as the radius is the same, is going to look the same. The field is going to look the same no matter where we are around here. And that's because of symmetry, simply put. So we know that the magnetic field is going to circulate around the current, and so we're going to say, okay, it's directed only in the phi direction. In other words, we're going to say that the magnetic field only has a phi component in this case. The next step then, after we've defined our Amperian contour or Amperian path, is to go ahead and take advantage of Ampere's circuit law in the following way. What we're going to be using this equation right here. Okay. Now again, like so many of the problems in this class, the trick is going to be figuring out for a particular geometry, okay, what's the form of the magnetic field, and then what is the form of this dl. All right, now dl in this case is a little tiny differential length that again occurs along a circle of radius rho. And if you look at some of the expressions in your textbook, you'll see that that little dl length is in cylindrical coordinates is equal to rho times d phi. So right there, that's where that rho d phi term comes from. This term right here, rho d phi in the phi hat direction, that is dl, and this term right here is simply h. So we're taking h dot dl, and we're going to be integrating it all the way around this contour. That corresponds to phi going from 0 up to 2 pi radians. Okay. All right, take the dot products here. We're saying that the magnetic field is independent of phi because of symmetry. So it actually comes out of the integral here, and you're just simply left with a very simple integral, the integral of rho d phi. Rho also is a constant, so that can come out. And then when you integrate d phi from 0 to 2 pi, you just get a factor of 2 pi. So in the end, the current enclosed by this Amperian path is just simply I. That corresponds again to this term right here. So I, the total current enclosed by this Amperian path, is equal to the magnetic field, the phi component of the magnetic field, times 2 pi rho. We can solve this little equation right here for h sub phi, and it turns out then that our total magnetic field, h sub phi, is going to be capital I divided by 2 pi rho. So the magnetic field is equal to I over 2 pi rho in the phi hat direction. That's it. So typically, Ampere's law is useful for solving problems that have a lot of symmetry. If you have symmetry, whether that's translational symmetry, rotational symmetry, whatever, you want to think about using Ampere's law if you're in the magnetostatic regime. Let's look at a more complicated problem next. This is an infinitely long coaxial transmission line. Okay. Let me explain what you're seeing here in this geometry. It's the coax of your experience. That's really what we're studying here is a coaxial transmission line. What you're seeing on the left-hand side here is this structure has an interconductor that's in blue. The interconductor of your coax is got a radius a. There's some kind of a gap here, in this case free space. And then you have another conductor right here, which is this other blue strip. Okay, blue strip has a width of t, all right, and an inner radius of b. Okay, outer radius is b plus t. Okay, so what's happening here? What's happening here is that current I is uniformly distributed over this entire cross section, and so you can think of it as the outgoing current is directed out of the page. So that dot means out of the page. So it's there. You have a total of I amps uniformly distributed over this cross-sectional area of basically area pi a squared. Okay, so this inner conductor that contains a total of I amps, and it's coming out of the page. Okay. You can think of, maybe this is a transmission line that's feeding some circuit. So I amps comes out of the page, flows through a circuit, does some work or whatever, and then returns back along this outer conductor here. See, there's an outer conductor, and it carries a current I amps into the page. X here meaning into the page. Again, we're assuming that this total I amps is uniformly distributed across this entire little blue annulus there. Okay. Well, how are we going to find the magnetic field everywhere in space due to an infinitely long coaxial transmission line? Well, let's start, and let's say that we're going to restrict our radial distance rho to be less than a initially. Okay, so we are going to get an expression for the magnetic field that is valid if and only if rho is less than or equal to a. All right, so in other words, we're in here, we're in this region. We're going to again argue by symmetry that because the geometry looks the same from every single angle around 360 degrees, that the magnetic field is independent of phi. It doesn't depend on the angle. Okay, so we're going to say again that the magnetic field is directed in the phi direction, and it is independent of phi. Okay, don't let that confuse you. It doesn't depend on phi, but it points in the phi direction. Okay. Okay, let's see what we can do here. Well, in order to figure out what the magnetic field is, we're also going to need an expression for, over here, the electric current density J in this region. Okay. You can sort of argue from units here in this way. If you have I amps that's distributed evenly over a circular area of radius A, then the electric current density, amps per meter squared, or amps per area, is going to be I divided by the area of this circle, pi a squared. Okay, and that's all they've done right here. This right here, I over pi a squared, that is just simply, or right here, that's just simply the current density in this inner conductor, the electric current density there in the inner conductor. Okay, so we're going to say then that we can write an expression for the electric current density in this inner conductor as I over pi a squared, all in the z direction, all flowing out of the page. Okay. We also have to integrate this thing over, we have to integrate the electric current density over this area. And again, if you want to look up in some of the expressions they provide in your text, you'll see that in cylindrical coordinates, if you want to integrate a circle over a circle, the expression for ds is equal to rho times d phi d rho, all in the z hat direction also, z hat. Okay, so if we want to get I enclosed, we have to compute this integral here. J is this, okay, electric current density is that, and ds we've decided is this. We take the two dot products and integrate from 0 to 2 pi, and rho goes from 0 up to a. That's what's happening right here. Okay, so just substituting in the appropriate expressions for capital J here and for ds here, and we get an expression that looks like this. We really, Sadhguru should have used a dummy variable here. Really what he should have done is say, we're going to integrate r dr from r equals 0 up to rho. Okay, so that's a little bit confusing. It's a little strange to see rho equals 0 up to rho there. Don't let that throw you. That's all he's really doing. Integral of rho d rho is just simply rho squared over 2. Okay, so he's just simply integrating and getting rho squared over 2 there, and then when he integrates d phi from 0 to 2 pi, there's a factor of 2 pi that comes out. The 2's cancel, and this expression results right here. The pi's also end up canceling, and you just get I rho squared over a squared. That's the total current right here that is enclosed by an Amperian contour at a particular value of rho such that rho is less than a. Okay, So basically we've worked on the right-hand side of this equation. Now we have to go back and work on the left-hand side. Again, when we're integrating h phi, we did this before over this little line here of a particular radius rho. You can set up the integral. The integral phi goes from 0 to 2 pi. dl again in this case is rho d phi instead of a d phi because this Amperian contour has a radius rho in this case. And so when you integrate around that, you integrate h phi around this contour, you just simply get h phi times 2 pi rho in this case. That's the left-hand side of this equation. And we go ahead and substitute this expression for I enclosed on the right-hand side, and we end up here. H phi times 2 pi rho is equal to pi rho squared over a squared. I can now solve this expression for h phi, voila. So the magnetic field, the takeaway here is if you have a coaxial cable that's carrying current I like this, the magnetic field increases linearly from the center of the conductor. So when rho is equal to 0 here, there's no magnetic field, in other words, at the very, very center. And then the magnetic field will increase linearly like that until we reach rho equals A. Okay? All right, now the question is, can we get an expression for the magnetic field when rho is between A and B in this region here in free space? Okay. This one is a little bit easier because we can set up our Amperian contour L2 right here. This is our second Amperian contour that we're going to use when rho is between A and B, when we're in between the two conductors, in other words. If you're going to work on the left-hand side of the equation there, it's the exact same expression. You'll be integrating h phi times rho d phi, phi going from 0 to 2 pi. That integral just gets you this. And no matter where what your radius is here, as long as rho is between A and B, you're always going to be enclosing the same amount of current, which is, in this case, the total current I right here. So when you're in this region, you end up with this little equation from Ampere's circuit law. You can solve this guy for h phi, voila. It turns out that h phi is I over 2 pi rho in this region here. Okay, so the magnetic field increases linearly up to that point, and then it starts to decrease in magnitude as 1 over rho in this region. Okay, one more region, well, two more really. The next one is rho between B and B plus T right here. When we're inside of the conductor, the outer conductor, what's the expression for the magnetic field in that case? Okay, let's set up our equations. We're going to define our Amperian contour L3 to be at some value, have a radius rho, such that rho is between B and T right here. Okay. Again, arguing that h phi is independent of phi. And now we have to think about what's the expression for the current enclosed by this contour right here. What's the expression for that? We know that this contour here encloses all of this current plus I. Okay, so the total I enclosed by L3 is positive I, all right, plus whatever current lies between the inner edge here at rho equals B and the Amperian contour at rho. Okay, so if you imagine again, if you think about this, let's imagine first of all that we have a total of minus I amps that's flowing through this entire outer blue conductor here, all right? So that's minus, if you want an expression then for the electric current density J in this region, what you have to do is take minus I and divide it by the area of this guy, all right? That's the area of a circle of radius b plus t, which is pi b plus t squared, minus a circle of radius b right here. So this bottom expression right there, that's just simply the area. So pi times this term in brackets, that's just simply the area of this blue annulus right there. Okay, so the current density in this region is minus I divided by that area right here, and it goes in the z hat direction. All right. Okay. Now what we're going to have to do is we're going to have to integrate this expression from rho equals b up to rho, and then all the way from 0 to 2 pi. So we want to know how much area is enclosed in this strip in between the Amperian contour and the inner edge at rho equals b. All right, and that's what's happening in this expression. Okay, so when we're in between here, when we integrate now, if you think about what's happening here, if we're integrating this expression, all of this stuff here is independent both of rho and phi. Okay, really, essentially, it's all independent of that. Okay, so when you integrate this thing dot ds, you can pull this entire expression out of the integral. All right, it's all going to come out. None of it depends on either rho or phi. So the whole thing is going to come out. And that's where this term comes from. When you do that integration on this side here to get your total I, so you get I, your I total I enclosed is this I from here plus the integral of this thing, rho going from 0 to rho plus t, and then all the way around, from rho equals a up to rho, and then from 0 to 2 pi. Okay, that's where this term comes from. When you carry those integrations out, you get that, and then you can solve for, once you've set h phi 2 pi rho equal to that current, you can then solve for h phi, and you end up with this expression here. Okay, that's what the magnetic field looks like inside this region. Okay, it's still falling off. I should say there is a term here that falls off like 1 over rho, but then there's also a term that increases here linearly in rho. So it's a little more complicated in that little strip. All right. Now, once you're outside, once rho gets greater than b plus t, and you're outside here, you got your last Amperian contour, which is equal to L4, which we're calling L4. Okay, let me go back. I missed my expressions. Here they are. Here they are. This is the, let me back up just momentarily here. So here's our expression for the current density inside this blue strip. And now, here we go. We're going to calculate our total I enclosed right here. It's I minus, again, here is our j. That all comes out of the integration here. And you're integrating from rho going from b, this distance there, all the way up to wherever rho happens to be, up to rho, okay, of ds, which is rho d phi. Again, you're getting a factor of rho squared over 2 from this integration, and you're going to get a factor of 2 pi when that all cancels out. When you cancel everything out and add it up, that's what you get for I enclosed. Now you're in a position to solve for h phi. Okay. Getting back to what happens then out when rho gets larger than this distance rho plus or b plus t right here, we want to know, okay, what's the total magnetic field outside in this region? It's a pretty simple argument. Again, you say h phi cannot depend on phi, and then you have to look at the right-hand side of the equation. How much total current is enclosed? Well, this current, this Amperian contour right here encloses negative I plus I, which is equal to 0. So When you solve that equation, right, this little expression right here, when you integrate the magnetic field around the contour, you actually have to set that equal to 0, which implies that outside h phi is in fact equal to 0. Okay. Understand that's a fairly complicated problem, but there's a lot of good things to learn there in that one. I encourage you to look in your textbook. They actually make a plot of the magnetic field as a function of rho, and so you can see what it does in each of these regions. And so you can clearly see on that plot that there's a linear region, a region when it decays a little bit, and then a more complicated region, and then it finally, once you hit rho is equal to b plus t, then the magnetic field magnitude actually does decline and go down to 0, just as is predicted here by the theory. Okay, thank you very much for your attention, and I'll see you in the next lecture.